All right, so welcome to kind of our 12-12 review session of sorts. We're going to be taking a look at kind of all the problems you guys have posted up in the discussion board and talking a little bit more about some of these topics, hopefully to kind of refresh ourselves from some of the things maybe earlier this semester that haven't seen in the last week or so. So I'm just going to kind of go through. I've got this a little bit sorted again by section in terms of topics. So I'm going to start with actually one from kinetics and taking a look kind of at this particular example. And so we're asked, what is the concentration of A after 50.5 minutes for the second order reaction A going to products when the initial concentration of A is 0.250 molar? And we're told that K is 0.117 molarity to the -1, minutes to the -1. So as a starting point for kinetics, there's a couple different equations. You have a whole bunch of different reaction orders that you can affect things as well. But in terms of getting started, anytime you see a kinetics problem that has a time involved, instantly you should be thinking about your different integrator rate laws. Like that should be your starting point. So you're going to be looking for an integrator rate law because we have a concentration and time both involved, and the only thing that really involves both of those pieces is going to be an integrator rate law of some sort. Now, for integrator rate laws, though, you do have the issue of what's your reaction order because there's different integrator rate laws for 0th, 1st, and 2nd order reactions. In this problem, we're told it's a second order reaction as part of the problem, but even if they didn't tell us this, we should still be able to figure that out. For instance, the fact they give us our rate constant down here and it's inverse molar, inverse minutes, like the molarity power basically tells you what your reaction order is. If it's molarity to the first power, that's 0th, molarity to the 0th, like if it's basically not there, if it's just like inverse seconds or inverse minutes, would be first order. In this case, molarity to the -1 is there for a second order reaction. So we could have actually told it second order just from these units, even if that wasn't included here. Now, in terms of solving this for second order reaction, then we can look up the second order integrator rate law, which is this that I'm writing over on the side that I can't see at the moment. There we go. So 1 over the concentration at some point in time t should be equal to positive the rate constant times that time t plus 1 over our concentration initially. Right, so that's effectively our integrator rate law. And we're asked, what's our concentration? So we're actually looking for our A sub t. At a time of 50.5 minutes, so there's our t, we have the rate constant given here for K, and they tell us the initial concentration is 0.25. So we're basically just plugging all of our pieces in here and just solving for our concentration. Right, so we have 1 over the concentration we're trying to find, should be equal to K, which is 0.117, molarity to the -1, minutes to the -1. Now, do pay attention to units on things, right? So the rate constant actually has inverse minutes here, and they give us a time of 50.5 minutes, so that's actually nice. Our time units match. They might not always match. And if the time units don't match, then pay attention to that, and you might have to do a conversion of some kind to make sure that they do match. And then 1 over our initial concentration here, and then now it's just a matter of doing a little bit of math, right? So I can take our rate constant times that time there. I'm going to get about 5.91 plus, what is that, 1 divided by 0.25 is just 4. So 1 over our concentration at some point in time is equal to 5.91 plus 4, or 9.91. But that means our actual concentration should be 1 over 9.91, which is, looks like 0.101 if we're going 3 significant digits. And since it's a concentration, should have units of molarity. So that would be our final answer in this example. But in terms of most of these problems for kinetics, it's all about setup, right? So if you have a problem that involves time in any way, shape, or form, it's probably going to be an integrator rate law type problem. It's possible maybe you could get something with a half-life, but even half-life type questions can usually be done using the integrator rate laws, for instance. And then you can actually just plug in, like if you're not sure what the half-life equation for something is, if you have the integrator rate laws themselves, which I believe are given for the ACS exam, you'll actually see that here for your initial concentration, like you can just put in 1 and you can put in 0.5 over here, and that will get you basically your half-life equation, or effectively kind of simulate the half-life equation. If you have other problems from kind of the kinetics chapter, since I don't think there's any other specific questions anyone asked, you can remember things like the Arrhenius equation and kind of how it's related to activation energy, right? And the fact that as activation energy goes up, the rate of your reaction goes down, your rate constant goes down. But the temperature also can affect things, and that higher temperatures will be higher rate constants or faster reactions in general. And so there's kind of some general trends, but your Arrhenius equation looks a lot like the Clapeyron one, and also had like the logarithms and things involved. So those are kind of some other things from that chapter maybe to review a little bit before our final exam. Now, I did have a number of questions about ice tables and assorted equilibrium type problems. So I have a handful here that I'll work through. A couple of these are ones from class previously too. But let's take a look at this first one here. So set up and fill out a ice table, find all the remaining equilibrium pressures, and calculate Kp for the reaction, given kind of some starting information for this large reaction. So the first thing I'm going to do, if I'm going to have to make an ice table, I'm going to go ahead and write my reaction out first. So I have N2O5, try to leave myself as much space as possible. N2O5 plus 2SO3 is going to, I think it's 2 SO2, yeah, 2SO2 plus N2O plus 3O2. Right. So there's my full balance reaction. And in terms of what I have to do, and it tells us in the problem that to set up a ice table, but it could just ask what are all of the equilibrium pressures and calculate Kp for all of the rest of this. And it might not even tell us to do the ice table. So how do I know I need to do that table to begin with? It's the fact that I have initial pressures that are given, and I'm given something else at equilibrium, which will also help. But it's really just that word initial. If we have initial amounts of something, and it's not a neutralization reaction, right, now that we've done chapter 17, like a neutralization reaction, you'd really do the BCAs before an ice table typically. So ice table is for equilibrium, which we have here, right? It's not an acid-base neutralization. So we're going to do an ice table, and we're just going to put in our initial pressures that we have. And our initial pressures are 0.175 and 2.45 for N2O5 and SO3. So, sorry, 1.75 and 2.45. Put those in. That means I have nothing for my products, which means my reaction has to go in the forward direction. All right, so for filling out my ice table, the biggest things here, pay attention to stoichiometry, right, for your changes, because for ice tables, we're not going to completion. So we write our change in terms of x. So reactants, if I'm going forward, have to go down, and they're going to go down by minus x and minus 2x in order for us to pay attention to stoichiometry. And then for the SO2, and in all of our products, these are going to be increasing. And again, pay attention to stoichiometry. So I'll have plus 2x for SO2, x for N2O, and plus 3x for the O2. And then for the end of this, then we can write our equilibrium amounts in terms of x to start. So 1.75 minus x, 2.45 minus 2x, and we'll have just plain 2x, x, and 3x. So there's our ice table that's fully filled out. Now, the other piece of information we're told is that the equilibrium pressure of O2 is 1.23 atmospheres. So how does that help us? Well, that means this value, 3x, actually equals that 1.23 atmospheres. So if I put that in over here, I can say for this part, 1.23 has to equal 3x. That means x equals 0.41. So I basically solved for my x without having to do a whole lot of work because they gave me one of the equilibrium pressures. And on top of that, since I now know x, I can figure out all the rest of these values. Right? So plugging that value in for x, I'm going to have the 1.23 for O2 I already know, 0.41 for N2O, 0.82 for SO2, 2.45 minus 0.82 is going to give me 1.63 for the SO3, and 1.75 minus the 0.82 is going to give me 0.93 for the N2O5. So I have all of these equilibrium pressures now, and now if I want to find my equilibrium constant Kp, right, it's products over reactants, but coefficients matter, right? So I have to pay attention to that. So for the SO2, I'll have 0.82 squared. For the N2O, I'll have just the 0.41, and for the O2, I'm going to have 1.23 cubed. All divided by then my reactants, so N2O5, 0.93 to the first power times 1.63 for the SO3, and then that's going to be squared. All right. Oh, and actually I've got one mistake here. Let me backtrack. This is incorrect. It shouldn't be 0.93 for that N2O5. I subtracted the 2x effectively instead of just the 1x. This should be, what should that be then? 1.34. So 1.34 right there. Sorry about that. All right, now I can go ahead and plug in all those numbers, and it's just some arithmetic at this point. So plugging all this in my calculator, 0.82 squared times 0.41 times 1.23 cubed divided by 1.34 times 1.63 squared, and I get about 0.14 at the end of this. So that's my KP. And remember, equilibrium constants, no units. So this one's not too bad in terms of going through and solving. If we didn't have one of these equilibrium pressures, that's when they would probably give us the equilibrium constant. And now we would be putting in all of our x's into everything. Realistically, for something like this where there's a bunch of cubed and squared terms, like the only way we'd be able to do that with our equilibrium constant is if it was really small, so we can make the x a small approximation. Because there's just too many coefficients and powers here that if we didn't have a way to ignore some of our plus and minus x terms, there's probably no way we'd be able to really solve the function at that point. At least not easily or not without graphing, which is not something you're expected to do for like tests that we normally would write in class or for like an ACS exam where you do have a limited amount of time. All right, so let's look at a few other examples of equilibrium type problems. We have some that are pH based and some that are actually just kind of more equilibrium based. So let's take a look at, we'll do one that is acid base based. So here we're told the pH for a 0.0715 molar solution of CCl3CO2H is 1.40. Determine the Ka value of that acid. All right, so how do we go about trying to set this one up? So normally we're finding the pH and we're given the Ka. Now we're kind of reversed, right? Well, if this is a weak acid, or we're looking for Ka, so it pretty much has to be a weak acid, we can actually write just a kind of a generic ice table equation, right? So I can say HA, and I'm just going to abbreviate HA as our acid in this case. Our weak acid should be dissociating into H plus and A minus. And really this H plus is the H3O plus. Like if I wanted to expand this, I could say, right, H2O plus HA making H3O plus. It's probably the better technical way of writing that. H2O being a liquid, so we aren't going to care about it in the table. Everything else is aqueous. And if you're wondering, like, why am I setting up this reaction? Well, if I have a weak acid, if I'm looking for Ka, that's an equilibrium constant, right? So I should be able to know this is the reaction that equilibrium constant applies to. Ka is always the acid plus water, making H3O plus and the conjugate ion. If we had a Kb, it would be basically our base plus water, making instead of H3O plus, we'd make hydroxide if we were working with a Kb, and then whatever conjugate acid would form as a result. So now, what I'm going to do here at this point is I'm going to plug in the values that I have. Water we don't care about, as we said. We have a 0.0715 molar initial concentration of HA. Nothing else is in a solution. And so I can set this up, and we can just, just like the last example, put our changes in. Oops. So 0.0715 minus X for our reactant, or HA. And then just X should be our equilibrium amount of our products in this case. And what we can do at this point is we have one other piece of information, right? We're told the pH is 1.40. So how does that help us? Well, pH is the negative log of H3O plus, so it's related to our H3O plus concentration, which means if I solve for the H3O plus out of that equation, if I take 10 to the negative pH, that should give me this H3O plus concentration. So 10 to the negative 1.40 power should be equal to the H3O plus concentration, which is also equal to X. And if I calculate that, I get about 0.0398, which is maybe more decimals than I need, but I'll go with that for now. That's how many decimals they gave in the initial concentration, so I'll leave that about the same for right now, even though technically there's only 2 decimals in my pH, so really this should probably only be 2 sig figs, so like 0.040 is probably technically correct by significant figures standpoints. I'll just go out to this because that's what I have decimal-wise here. And so now as I put everything together, I can plug that in for my X value, right? So I can take 0.0 715 minus 0.0398, get this will be then 0.0317. And then my other two x's are just, it's a 0.0398. And now for my Ka value, right? So my Ka value is now going to be products of a reactant, so 0.0398 times 0.0398, all divided by 0.0317. And I get about 4.9, actually, if I want to, it's going to be 5.0 times 10 to the minus 2, which is actually pretty large in terms of Ka, but I have a pretty tiny concentration. My pH is 1.4, which is awfully low, so it kind of makes sense that this is a relatively large Ka, at least in terms of weak acid comparisons. Most Kas for a lot of weak acids are usually going to be something more along the lines of like 10 to the minus 5 or smaller for the majority of them, but there are a couple that are a little bit higher. And if you want to think about like structure things, which I'll kind of review this a little bit here actually, right? The structure of this compound actually looks like this. And so the question that we can also think about is, why does this thing have a Ka value that is fairly large in terms of weak acids? Well, there's one really easy kind of answer to this. If I were to take off this proton, right, that's the only proton there that can be lost. If I take off that proton, what's left? Well, if I get rid of this and take off the proton, I have an oxygen with a negative formal charge. But because I have oxygen with a double bond here, I actually have resonance. Right? And so the resonance that's present here is what actually helps stabilize this overall ion. And the more stable this big ion is, the stronger the acid's usually going to be, the easier it is to lose the proton. That's why our Ka is reasonably big. We have some resonance stabilization, and kind of as an added bonus, we have these chlorines over here too that can help kind of pull some of that negative charge away because these things are pretty electronegative. So we have a lot of things there that actually help distribute that negative charge that make this whole ion pretty stable, which means it's easier to lose the proton in the first place and makes it a stronger acid. So, and that line of thinking, it's helpful if you get that right now for 1212, although probably not the end of the world, but it'll be really helpful if you can kind of reason through that and make sense of that when you get to organic. And organic will spend more time exploring those kind of things as well, but it's just kind of a useful thing to start thinking about now, and more often than not, resonance is kind of a key to a lot of those kinds of features. Okay, so let's move on. We'll take a look at one last equilibrium, just kind of straight equilibrium problem. So here we're told for the reaction below, Kc is 9.2 times 10 to the minus 8, and we're asked what is the equilibrium concentration of D if the action if the action begins with 0.48 molar of A. Okay, so looking at this problem, we're asked for equilibrium amount, and it begins with some amount, so that's kind of like an initial quantity of some kind. So that means if we have an initial amount, we're going to have to do an ice table. So we can write our reaction of A plus 2B is going to C and 2D. Now, for our ice table, there's one big important thing we need to pay attention to. It only gives us an amount of A, and that's it. Well, why does it do that? We only have this initial concentration for A because our other reactant B is a solid, and so is C actually in this case, which means in terms of putting in values to my ice table, I don't care about solids, right? So I can actually just put in 0.48 for my concentration of A. I don't have any D to start. And now change again, it's in terms of X. So minus X on my reactant side, I have to be going forward because I have no products yet. So plus 2X on the product side, we'll give 2X and 0.48 minus X. And we're told in the problem that Kc is 9.2 times 10 to the minus 8, which is pretty tiny, right? Really small equilibrium constant. X is the amount we're going forward, so it's probably not going to be very big, so we should be able to do the X is small approximation here, right? Because we're going to have 2X, and we're going to have that whole quantity. This is important. It's actually really important. The whole quantity of 2X is being squared, so I have 4X squared on top, all over 0.48 minus X. But if we use X is small, that basically means we get to ignore the minus x portion. Right? That's the part we're ignoring. And now I have a lot easier math to solve for the x. So I can multiply the 0.48 across. This will square out to 4x squared overall, so I can divide the 4 over and take the square root of everything to get my x value. And so if I solve for that x, let's go ahead and solve for that. 9.2 to the minus 8 times 0.48 divided by 4, and then take the square root of all of that. And I'm going to get about 1.05 or 1.1 times 10 to the minus 4th is what it looks like. And that's my x value. And it wants to know the equilibrium concentration of D. Well, D is 2x, so that means that my final concentration here, concentration of D equals 2x, so that's going to be 2.2 times 10 to the minus 4. And since it's concentration, it should have units, it's going to be molarity in that case. So again, general setup, and you'll see we get spoiled a lot, you being able to use the x is small. That's not really an accident. Like most times that we're doing equilibrium problems, like especially if it's acid-base related, x is small is going to be there and available to us, it's going to work. In this case, had that been like 10 to the minus, 9.2 times 10 to the minus 3 instead of the minus 8, we wouldn't be able to do that, and we would probably have to go the quadratic route. I would like to say that the ACS exam won't give you anything with the quadratic on it. However, it is possible. I've seen it in the past, although it's usually pretty uncommon. They usually give things that x is small is going to work for, but keep an eye on that. And again, the big rule of thumb, I use this approximation pretty much any time where the equilibrium constant is at least 3 powers of 10 smaller than whatever initial concentration you're adding or subtracting your x's to or from. And so that's what I'm looking for. This is really like 10 to the minus 1 over here. This is 0.48. This is 10 to the minus 7. I'm sorry, 10 to the minus 8. So that's a 7 power of 10 difference between the two. So equilibrium constant is plenty small in this case to make this approximation to help just make the math a little bit easier on us. All right, so the next section of problems I have is actually titrations. I had a handful of people I think ask about these as well. So you'll see I think I have like 3, maybe even 4 problems on titrations here we'll take a look at. So some of these will be short, some of them will be a little bit longer because there's a lot of different variations of things we can see with titrations. So for the first one, we have 33 milliliters of 3 molar hydrochloric acid is titrated with sodium hydroxide to form water and sodium chloride. It asks how many millimoles of sodium hydroxide are consumed to be able to do this. Well, I'm assuming that, and this problem's a little bit vague, honestly, in how it's being asked. I'm assuming that you're talking about how many millimoles are needed to completely neutralize the HCl. Because otherwise, if it's not how much are going to be to neutralize this, we would need like some starting concentration or volume of the sodium hydroxide being used. So since they don't give us that, I assume it means we're just neutralizing all of the hydrochloric acid. And so if we're trying to figure out how many moles of the sodium, in this case it asks millimoles, how many millimoles are going to be necessary, we just need to figure out how many moles of HCl we actually have, right? Because HCl and NaOH should react in just a 1-to-1 ratio. Right, like that. And that's important that I showed this is a 1-to-1 ratio, because if this was not HCl, let's say it was like sulfuric acid, it'd be H2SO4 plus NaOH. That's important to know because it would take 2 sodium hydroxides to neutralize all of the acid in the balanced reaction. And so that would change how many millimoles of the sodium hydroxide we would need if our acid had more than 1 proton, for instance. But in this case, it doesn't. It's 1-to-1, so that actually keeps things kind of easy. So this means, like, basically for full neutralization, our moles of HCl should equal the moles of sodium hydroxide. And for our moles of HCl, this we can find by just taking our volume times our concentration. So 33 milliliters. I rarely ever work with millimoles, so I'm just always in the habit of writing things in liters. So 0.033 liters times 3 molar. And if I multiply that out, that's going to be 0.099 moles. Or if we're working in units of millimoles, the reason you see them sometimes get used is you can actually just take milliliters times the concentration, and that effectively will tell you millimoles. So if you took this as 33 times 3, this is going to give us 99 millimoles. Which, if I convert my moles the normal way that we would find moles here, I can just multiply this by 1,000 to figure out how many millimoles I have, and I would get that same 99 as a result. So I need 99 millimoles of sodium hydroxide to neutralize all of that HCl in this case. All right, let's look at some more titration type problems. Let's take a look at just the next one. We're just going to do them in order. So consider titration of a 24.0 milliliter sample of 0.105 molar acetic acid with 0.130 molar sodium hydroxide. It asks A, what is the initial pH? So this is actually pretty similar to kind of like the titration page that I sometimes have on tests. But for the first part of this, initial pH. So initial pH would be before any sodium hydroxide gets added. All we have is acetic acid. How do we find the pH of acetic acid? Well, we're going to have, first off, the Ka value, which they do give us down here. So we're going to need Ka for acetic acid. So they're using 1.77 to the minus 5. We've probably used 1.8 to the minus 5, I think, in most cases, which is also fine. So for us, we're told Ka 1.77 to the minus 5. Right? We have a weak acid. It's 0.105 molar. So how do we find pH? Well, anytime we have just a weak acid or just a weak base in solution, how would we normally find pH? It has to be an ice table, right? So if I set up an ice table, I would have my acetic acid, and again, I'm just going to abbreviate to make my life a little bit easier here. And technically, again, H plus really would be the H3O plus. They are the same if I added water as my other reactant, but I'm just going to make things, again, a little bit easier here. So 0.105 is my initial concentration for the reactant. It's going to go down because I have to go forward. I have no products yet. So plus X on products. Right, so that's going to give me Ka of 1.77 times 10 to the minus 5 equal to X squared over 0.105 minus X. Well, remember, I said 3 powers of 10 is the cutoff. This is really 10 to the minus 1. This is 10 to the minus 5. It's 4 powers of 10. X is small should still work. So I can use the X is small approximation to ignore that minus X. Again, make my math a lot easier for myself. So I can take 1.77 to the minus 5 times 0.105, and then I can take the square root of that, and I'll have my X, which looks like it's about 1.4 roughly, times 10 to the minus third. All right, and now if I want pH at the end of all of this, right, pH is the negative log of H3O plus. Well, X is the H3O plus concentration. Right, so negative log of 1.4 to the minus 3. And I get about 2.85, it looks like. So 2.85 would be my pH for that acetic acid solution. All right, question part B of this one asks, what's the volume of base added to, what volume of added base is required to reach the equivalence point? So how much base am I going to have to add? And so this is a case where if we look at our reaction, I have acetic acid and sodium hydroxide. I have 1 proton and acetic acid it can lose. I have 1 hydroxide and sodium hydroxide that it can use for neutralization. So since this is a 1-to-1 ratio, you can basically do what I had showed previously when we talked about this, is you can do M1V1 equals M2V2. Right? You can set things up this way, which is normally used for dilutions and dilutions only. But the idea is this can work if it's a 1-to-1 ratio for your acid and your base for any neutralization. Because your moles, the reason this equation gets used for dilutions is that your moles at the start of your dilution, the moles at the end should be the same for your solute. Well, in this case, if it's a neutralization between an acid and a base, the moles of my acid should equal the moles of base if it's a 1-to-1 ratio in the balanced reaction, which it is since I have just the 1 proton and the 1 hydroxide for each of them. So I can use this equation to kind of simplify things. So what I can do is I can find the volume, V2 here, right, for the sodium hydroxide should be equal to M1, the concentration of my acid, which was 0.105 molar, times its volume that we had, which was 24.0 milliliters. And I can actually get away with leaving this in milliliters if I use this equation, because it just means the final answer I get will have units of milliliters. And then the bottom concentration for sodium hydroxide was 0.130. And now I can find that volume that I'm going to need. So 0.105 times 24 divided by 0.130. Oops. And I get about 19.4. So 19.4 milliliters. That's the volume of the base that I'm going to need to get to the equivalence point. All right, I have a few more pieces of these. Part C, so the pH at 6 milliliters of added base. So now that I've started adding base, I'm going to have base, the sodium hydroxide, and my weak acid both present. What's going to happen? Well, if I have an acid and a base, these are not a conjugate pair. That means neutralization, right? So that means I have to do a BCA table. So I'm going to start with, again, I'm just going to leave my acetic acid as HA for all of these. And I'm reacting this with sodium hydroxide, which I don't like including the sodium because it's just a spectator ion. So it's really HA plus OH minus. It's going to be making H2O, and in this case, A minus. Right? And I think this way it's easier to see HA and A minus as a conjugate pair than if you have the sodium there. It just sometimes makes that maybe not as easy to immediately recognize. All right, now for me to use the BCA table, what do I have to do? I have to put things in terms of moles. Right? So for moles, for the acetic acid, I'll have 0.105, its concentration, times its volume in liters, so 0.024. So I'll get 0.00252. So there's my moles of HA. For my sodium hydroxide, I'll have 0.130, its concentration, times 0.006, its volume. I'm going to get 0.00078 moles of the hydroxide. And this is why sometimes, like if you have like Dr. Fuller or some people, they often just work in millimoles. And you can say you have 2.52 millimoles and 0.78 millimoles to have not so many zeros or maybe powers of 10 involved. But at the end of the day, it's not really going to change anything in terms of your final answers. And we'll kind of see that as we get to the end here. Now, for the conjugate base, we don't have any to start with. Now, change for BCA tables, remember, is just whichever of these is smaller. So that's going to be the hydroxide. We're going to subtract that amount from both our reactants. And so if I do that, I think I get, what is this, 0.00174, I believe. And then the other one I'm going to get 0 for the hydroxide. And then I have 0.00078 of my other conjugate ion over here. So at the end of my BCA table, what we should always be asking ourselves is what's left? Well, I have a weak acid, right? And I have its conjugate base. So if I have a weak acid and a conjugate base, those together make a buffer, which means if I want to find my pH, I can use the Henderson-Hasselbalch equation. pH is pKa plus the log of the base over the acid. Right, and so if I'm going to plug all my pieces in here, pKa, so negative log of my Ka, which is 1.77 to the minus 5 is what they gave us for acetic acid, plus the log of my base, which when they ask for that, it's the final amount of the conjugate base in your BCA table. So 0.00078 divided by the 0.00174 for my acid. Let me check and make sure that is the correct value. I'm not messing up my mental math here on a Sunday morning. Okay, not going crazy. And now I can plug all these numbers in and calculate my pH. So negative log 1.77 to the minus 5 plus the log of 0.00078 divided by 0.00174. And I get a pH that's about 4.40 at this point. All right, so that was a decent bit length for that particular question, right? Finding basically the pH partway to the equivalence point. Now for part D, it asked me what is the pH halfway to the equivalence point. Turns out this part's really, really easy, right? Because if I'm halfway to the equivalence point, and if we think about kind of just from a theory standpoint, halfway to the equivalence point would mean that my moles of hydroxide are half this amount, which means at the end of my BCA table, the amounts of my HA and A minus that I have should actually be the same. Which means if I go to use this Henderson-Hasselbalch equation, if the base and acid amounts are the same, this ratio is 1, the log of 1 is 0, that means pH just equals pKa. So all I have to do to find the pH halfway to my equivalence point for this weak acid titration is just take the negative log of 1.77 to the minus 5. And that's going to be about 4.75. So I get a pH of about 4.75, halfway to my equivalence point. So that part's easy. Part E, unfortunately, is not so easy, right? And this is probably the hardest part of all titration problems, is finding the pH at the equivalence point for something. So we'll go through, kind of review all of our steps for going through this lengthy process. So at the equivalence point, there's some things we want to kind of recognize, right? At the equivalence point, that's when all of our moles of HA have reacted, and the amount of OH minus is the same, right? These two values will be equal. They will both be 0.00252, which will be 0 left over, 0 left over, and that means that we'll have just 0.00252 moles of A minus, right? So we could fill out the whole BCA table to show that, but if you recognize that all of your acid is going to become your conjugate base, that means I just know this is how many moles of my conjugate base that I'm going to have at the equivalence point. Right, so how does that help me? If all I have in my solution at this point is a weak base, how do I find the pH? Well, earlier we said that if there's only a weak acid or only a weak base, that's an ice table to find your pH. So I am going to do an ice table, but what's my reaction? Since A minus, you said, is a weak base, that means that I'm going to put A minus with water, and I'm going to be making my conjugate acid and hydroxide as my other ion. And so I'm setting up this ice table. The only other thing I have to be careful of is the values I'm putting in here for my ice table do have to be concentrations, right? So my concentration, I'm going to show this kind of over here up in the top right. My concentration of A minus at this point should be those moles, 0.00252, over my total volume, right? My total volume is going to be 0.024, plus that 0.024 is the initial volume of my acid solution. And then to that, I'm going to add how much I calculated earlier, this 19.4 milliliters in liters for units. This is the amount that it took to get to the equivalence point. So I add this to the 24 milliliters I already had. So by adding 0.0194, now I can find what is my concentration of A minus to put in to start my ice table here. So 0.00252 divided by 0.024 plus 0.0194, and I get 0.058 as the initial concentration of A minus. Okay, so from here, still have a little bit of work left ahead of me. I can ignore the water. I have no products yet. So minus x plus x plus x. And now to solve for my x, I need the equilibrium constant. Well, where am I going to get that part from? Because this is a reaction for a base, which means what I need is a Kb. Right? Well, Kb is equal to Kw over Ka. Since I don't have the Kb value right offhand, but I do have the Ka value of its conjugate, right? Since A minus and HA are the acetic acid's conjugate base pair, I have the Ka of the acid, 1.77 to the minus 5. So that means I can find my Kb. And it looks like my Kb should come out to about 5.65 times 10 to the minus 10. So 5.65 times 10 to the minus 10 is going to be equal to x squared over 0.058 minus x. And I can simplify this math for sure and use x as small. Right, 10 to the minus 10, really tiny equilibrium constant here. So I can move my 0.058 across. So 0.058 times, so I've ignored that minus x, 5.65 to the minus 10. And then I can take the square root of that to find my x value. So I get an x value that's coming out to about 5.7 times 10 to the minus 6. Now, be careful here because this is not my H3O plus concentration, right? X is the hydroxide concentration in my solution right now. So this is the hydroxide amount. So if my end goal is to find pH, I can find pOH by doing negative log of 5.7 to the minus 6. Which is about 5.24. And then my pH should be 14 minus that, or about 8.76. is what it looks like for my final pH. So 8.76 would be my pH at the equivalence point for this titration. So again, this is kind of the longest steps of these types of calculations. Right? Had to kind of understand from the beginning that this was the number of moles of my conjugate base I should have at the equivalence point, because all of my starting acid base and base are gone, which means that at that point, if I have just this weak base left, I need an ice table so I can write a reaction for that. But that means I'd also need a concentration that I have to find, so I can take the moles of my conjugate base from the BCA table, divide that by the total volume at the equivalence point, and so that may require finding the volume to get to the equivalence point if that was not given initially, to find this concentration here, which I guess I can write that in over there. Just to show where the starting number in the ice table came from. And then once I can set up my ice table, which I'm going to be making hydroxide since it's a base, I'm going to need Kb to be able to find my X, which I can find using Kw and Ka. And then I can solve for my X out of that table, which is the hydroxide concentration, not H3O+, which gives me that extra step that once I find POH, I can find the pH by subtracting that from 14. So a lot of steps going on there to find that pH. But at this point, all the individual pieces should be things we're comfortable doing, right? Like finding a Kb from a Ka value, or just setting up and solving an ice table is things we should be comfortable doing. But it's just kind of a number of things kind of in sequence that all have to be done to eventually get to that equivalence point pH. All right. So I think there's actually a couple more examples here. So let's take a look at, here we have the molarity of an acetic acid solution. Calculate the molarity of an acetic acid solution if 34.57 milliliters of the solution are needed to neutralize 25.19 milliliters of 0.1025 molar sodium hydroxide. So this is the actual practical application for most titrations that you would actually be doing like in a lab setting. And that's finding an unknown concentration. So how do we actually solve this? Well, first off, this problem is actually already giving you a big hint. It's already giving you the balanced neutralization reaction. If you don't have this at the start, that is the very first thing you should do so that you can see, is it a 1-to-1 ratio of acid and base or not? Because if it's a 1-to-1 ratio, you can get away with doing that M1V1 equals M2V2 again. If it's not, then you have to do more of a kind of a stoichiometric approach, like something out of like maybe say chapter 3 or 4 from 1211. Just basically it's a kind of simple solution stoichiometry. But in this case, since it is a 1-to-1 ratio, we can actually get away with just doing kind of like that M1V1 equals M2V2. Right, so we have, and again, I get to use this because at where we kind of fully neutralize everything, my moles of acid and moles of base should be equal, and that's how we can kind of treat these. And so I want the molarity of my acid. I'm basically looking for M1 in this case. So M1 should be equal to the concentration of the base, which is the 0.1025, times its volume, which was 25.19 milliliters. And again, I can leave this in milliliters as long as I use the volume for the other one, also in milliliters, 34.57. So that this way my units cancel out for the milliliters. I'm going to get a concentration in molarity. And this M1 for my unknown solution, 0.1025 times 25.19 divided by 34.57. And I'm going to get about 0.075. And if I'm looking here, it actually looks like I want 4 sig figs for all of this. So actually I can give more here. So 0.7074, oops, 7469 looks like. I'm doing 4 sig figs because I have 4 sig figs in everything here. It's unusual to have that many, but there would then be my concentration of my acid. If this was not a 1-to-1 ratio, instead of doing M1V1 equals M2V2, kind of the alternative way of setting that up and kind of working through it would be to actually instead take, you can start with your volume and concentration here. So I could say like 0.02519 liters times 0.1025 moles of the sodium hydroxide over 1 liter. And then what I can do is I can make a mole-to-mole ratio for the moles of my sodium hydroxide to the moles of my acid, which in this case was just the acetic acid. I'm just going to label it again HA for short. And now I can make a mole-to-mole ratio. In our case, this was 1-to-1, right? say we had something like sulfuric acid instead. If I had sulfuric acid, that's H2SO4. Now this ratio would be 1 to 2 to figure out how many moles of the sulfuric acid I must have. And so that's why that balanced reaction part's really important. And again, if it's a 1-to-1 ratio, you can just do the M1V1 equals M2V2. It's probably just faster. But if it's not a 1-to-1 ratio, kind of just setting up like a normal stoichiometry problem is probably more efficient, right? Because once I'm in moles of sulfuric acid, if I want the molarity, I can take the moles of sulfuric acid divided by the volume that they give me in liters to find that molarity as my last step. All right, one final problem, and actually I don't know if I'm going to actually do this one just because it's really, really long and it's almost identical to the one I did up here. Right, consider titration of 35.0 milliliter sample, 0.175 molar. This is acetic acid actually again with 0.200 molar sodium hydroxide. Find the pH at the equivalence point. So I guess I can go through, I'll try to go through this kind of quickly since we've kind of done this almost exactly once. But the biggest thing here is the fact that we have an acid plus sodium hydroxide. So we're making water. It'll be our conjugate base, the A- in this case. And if I'm going to do this, this is going to be a BCA table. And I'm going to show the full BCA table here, but if you recognize that you're at the equivalence point, you might not need to do this full BCA table, right? Because I'm going to need to find the moles of my acid. So 0.175 molar times 0.035 liters. So this will be about 0.006125 moles for HA. For the sodium hydroxide, if I'm at the equivalence point, it's going to be the same amount. Right? So they're both going to go down by that same amount, which means there's nothing left of my initial acid or the base. Everything has now been converted to the A-. So why is that important? Well, at this point, I have the moles of A-, and that's the only thing that's left. It's a weak acid problem now. So to get that weak acid problem started, I will need an ice table, but I also need the concentration of A-, which I'm going to get by 0.006125 moles over my total volume at this point, which is going to be the volume of my acid, 0.0350, which we have. And then this other part, I need to know how many how many liters of the sodium hydroxide I have to add to get this many moles. Well, if I know I need this many moles, and I know the concentration is 0.2 molar, right, I can take this number of moles, 0.006125, I can divide it by a concentration of 0.2, which gives me about 0.0306 liters of NaOH that are needed to reach the equivalence point. Right, and so that's going to have to get plugged in here. So I need that piece of information. It wasn't part of like the previous problem anywhere, so I have to actually find that as part of my problem, which is, again, just one extra thing to add to these equivalence point problems that does make them fairly long. And now from here, I can make an ice table because if I have a weak base, the way I find my pH is an ice table. Oops, it's going to be hydroxide and water. Oops. Not hydroxide and water. Man, I'm struggling here. It's going to be hydroxide and my conjugate acid for my ice table. And so as I set this up, I have my initial concentration here. Well, I had the numbers and didn't solve for it. So let me find that concentration real quick. It's about 0.0933. I have no water. I'm sorry, the water I don't care about. I have no hydroxide, no HA at the start. Standard change, right? It's an ice table now. My changes are x's. So minus x and then plus x and plus x. 0.0933 minus x, x and x. And again, for my equilibrium expression, I actually don't want Ka, I want Kb, right? Which is going to be Kw 1.0 to the minus 14 divided by my Ka, and the problem was 1.8 to the minus 5, which is 5.56 or 5.6 roughly to the minus 10 for my Ka, or sorry, for my Kb. Ugh, can't talk. So this is my Kb that applies to this reaction now that I can set up is equal to x squared over 0.0933 minus x. I can use x as small. Right, should look pretty familiar at this point to a lot of the steps we're doing here. So I can solve for my x value here. After I make the x a small approximation, my x is like 7.2 times 10 to the minus 6, and that is my hydroxide concentration again. So now I can find my POH by taking the negative log of that. And then my POH is about 5.14, which makes my pH, 14 minus that, about 8.86. So I do my final pH. So very similar problem to the other one that we had done. Slightly different pH, but it's pretty close to about the same equivalence point pH as the other acetic acid problem. Slight difference in the volumes and concentrations of things used, and a tiny difference in the actual Ka that was given to us as well. But those are, again, kind of all of our series of steps. Okay. I think that covers all of our major titration examples. I have a couple more just kind of individual questions from some different sections that people asked that I'll take a quick look at. And so this one is kind of more general acid base, and it's really actually more of like kind of acidity and basicity of salts. So it asks, which of the following 1 molar solutions would have the lowest pH? All right, so if we want the lowest pH, that means we want the most acidic salt. So if I'm looking at these compounds, how do I know which one's going to be the most acidic? Well, the best way to do that is break these things into their individual ions and just figure out, are they acidic or basic at all to start with? And then if they are acidic, we can use the Kas of the acid, basically the cations in those cases, to check. So going through each of these, I'm going to just kind of break them each down to their ions. Right? So the very first one was, I'm going to slide this over so we can see them all. Looks like lithium nitrate. So LiNO3, if I break this apart, I'm going to have lithium plus, NO3 minus. And the way we figure out, are these things like acidic or basic or neutral, for our cations, if I have a metal cation, I'm basically adding hydroxide, right? So lithium hydroxide, this would be a strong base, one of our group 1 hydroxides. And that means that my lithium ion itself is neutral because its conjugate's a strong base. For nitrate, its conjugate, the anions I think are easier. You always just add a proton. We get nitric acid, which is a strong acid, which means that nitrate is neutral, which means my whole salt is neutral. So I have a neutral salt for the lithium nitrate. All right, let's look at our next example. We have HONH3 Br. So this is a little bit awkward maybe to understand how it's being broken apart, but we are basically getting a cation that's HONH3 plus, and we're having Br minus. So Br minus is the easier one here, conjugates HBr. Well, HBr is one of our strong acids, so Br minus is neutral. All right, so what about this guy? How do I know what's going on with this guy? If you have nitrogens and a positive charge, its conjugate's going to actually be losing a proton, right? It's only the metals that we're adding the hydroxide to. So this thing's conjugate would be HONH2. And just by looking at it, you might not recognize that this thing is a base by looking. Although anytime you have nitrogen and it's not positively charged, it's probably a weak base of some kind. But we do notice in our chart over here, we do see that exact compound. HONH2 has a Kb value of 1.1 to the minus 8. Well, that means that this compound is a weak base, right? So if this is a weak base, the ion that it's making must be a weak acid. And in particular for that weak acid, we could even find that Ka, right? If I have Kb 1.1 to the minus 8, I can take Kw 1.0 to the minus 14 and divide by that Ka value that they're giving me, the 1.1 to the minus 8, and I get a Ka of about 9.1 to the minus 7, right? So this thing is acidic with a Ka value of 9.1 to the minus 7 for the acidic cation. So now I can look at my remaining two, right? So for option C, I have H2NN H3 ClO4. So if I break this up, that's going to give me H2NN, H2. Oops, no, that is getting ahead of myself. This is still H3, and this is plus, it's a cation. And we have the perchlorate, ClO4 minus. All right, now for these. Again, conjugates, the anion I think is easier, just add a proton. That's perchloric acid, so again, this is a strong acid, which means that the conjugate must be a neutral anion. And here I have another compound that has a bunch of nitrogens in it and hydrogens, so with a positive charge, if I take a hydrogen off, it's going to be H2NNH2, which if I look over here in my table is one of these compounds that's also a weak base. And its Kb is 1.3 to the minus 6, which means if that's a weak base, my conjugate is a weak acid. And the Ka, and I'm interested now in the Ka of my actual cation, right? So the Ka of that thing, again, I can take Kw, 1.0 to the minus 14 divided by the Ka of that, I'm sorry, the Kb of that conjugate base, 1.3 to the minus 6. And I get about 7.7 times 10 to the minus 9. So I do have an acidic salt, but if I'm comparing these two salts, I can compare their Ka values if they have the same concentration to know which one is stronger, to know which one should have a lower pH. And so looking at these two, so far this one has the bigger Ka value, so it should be more acidic, which means a lower pH. So right now this is winning. We have one salt left to look at, and that's CaBrO2. So if we look at this very last one, breaking up to its ions, I have calcium 2 plus. Well, calcium 2 plus, its conjugate, since it's a metal ion again, is going to be calcium hydroxide, which typically is considered a strong base, which means that the calcium ion itself is neutral. I can look at my anion, which is going to be BrO minus. Conjugate acid is going to be HBrO, which is a weak acid, which makes BrO minus a weak base. So this whole salt is actually basic, which means it will definitely not have the lowest pH. So having gone through all four of those, the one that should have the lowest pH is the one that's acidic with the biggest Ka value for that cation, which is going to be this H2 NNH3. I'm sorry, I just circled the wrong one. So let me get rid of that circle. It's the one above it that actually has the bigger Ka value. There we go. So the HNO H3Br, this compound should be the most acidic and have the lowest pH of all of these ionic compounds. And it's a little strange to kind of see this as acidic at first. The table is actually meant to help. The fact that we have like HONH3 and we have HONH2 that has a Kb value, meaning this is a base. If it gains a proton, it's going to make that for a cation. So we kind of have to put some of those pieces together. This is not a compound I would expect everyone to just know is, oh, it's a +1 cation by looking for general chemistry. That's not something we'd necessarily expect. But with the table here to kind of help out, hopefully that helps you kind of recognize that fact a little easier and see that all of these are actually just ionic salts. And we can figure out of those salts like which ones are acidic or basic or neutral. And if we're looking for the lowest pH, we want the most acidic one. So out of the two that were acidic, which one has the bigger Ka value using kind of the Kb's to get the Kas of the conjugates. So that is a decent bit of work to kind of piece your way through that from a conceptual side. So that's a good question to kind of go back and hopefully review for us and kind of see that walkthrough example. So last couple examples then to move on. I want to take a look at one redox problem. And so this redox problem, I'm going to talk about a couple things. Balancing this particular redox one is pretty awkward actually. And I'll kind of talk about why that is in just a second, because we don't have kind of our standard setup here in terms of easily being able to break apart our half reactions. Right? We're used to being able to do half reactions that we can break apart and do kind of keep the elements together. This one, I would say this is the example that was actually posted. So this one, it's kind of out of the norm. I would never expect you guys to probably have to balance this for this particular class. Higher level classes, we could probably get into this pretty easily in terms of balancing, because we can kind of hopefully break it up a little bit and just think about like what's really happening. And so I will do a little bit of that, but really what I'm going to talk about is kind of some general redox things. This is a redox reaction, but before I go to any kind of balancing and kind of why it's more complicated than normal and show how you can still do it, let's actually just look at things like what's oxidized, what's reduced, and what our oxidizing and reducing agents are for this reaction. So how do I identify that? Well, there's a few things going on here. So first off, if I'm going to identify all my oxidation states, I'm just going to write out this reaction. So I have AU plus NaCN plus O2 plus H2O, making Na AuCN2 plus then sodium hydroxide, NaOH. All right, so oxidation states. Gold Au initially is just 0. And then when I have, remember, when you have ionic compounds, break it to the ions first. That'll be really important over here. So breaking up to ions, I'm going to have sodium plus 1, Cn minus. And now oxidation states for something like Cn minus, following kind of our normal rules, the nitrogen technically there is plus 3. Cyanide is technically, I'm sorry, not plus 3 on the nitrogen, minus 3 on the nitrogen. Because the nitrogen is going to be before the carbon in that order. Carbon's going to be plus, I guess technically plus 2 here to balance. It's a little awkward. The good news is, as I'm kind of showing this, sorry, I'm kind of cutting things off here. As I'm kind of going through this and assigning these oxidation states, if I see that I have a polyatomic ion on the reactant side, and it's still the same polyatomic ion on the product side, their oxidation states probably aren't going to matter because it's not changing. So these aren't going to be that important to what's being oxidized or reduced for the most part. Here I have O2, so I'm again going to have a 0 oxidation state for the oxygen there. For water, I have plus 1 on the hydrogen, minus 2 on the oxygen. Product side, I'm going to have over here sodium again, and that means that all of this is really Na plus, then I have Au. This will actually be if I have 2 Cn minus, right? Cn minus, and I have 2 of them. Oh, here, let me write that in a better way. And the reason I'm breaking this apart is, again, because it's ionic. Right? Everything there is ionic. That means gold is actually just plus 1. And then I have the sodium hydroxide, where the sodium is plus 1, the oxygen's minus 2, and the hydrogen is plus 1. So this is probably a much harder than normal example for picking this out. But in terms of what is oxidized, I need the element that lost electrons. So if I look at each element one by one, gold went from 0 to plus 1. That's the one that lost our electrons. So I can say Au is oxidized. Right? It goes from 0 to plus 1. Sodium was plus 1 first, and it stayed plus 1. Cyanide was plus 2 and minus 3, but it stayed as cyanide on the product side, so its oxidation states will still be the same, plus 2 and minus 3. The gold we already covered. So then I have the oxygens up here, right? Sodium's still plus 1, oxygens minus 2, which one of them was minus 2, but I had some oxygens that were actually 0 to start, so that's actually what is getting reduced. Right? So oxygen is being reduced, the O2 going from 0 to minus 2. Now, other terms, things like the oxidizing agent or reducing agent. Well, I'm going to look for if gold was oxidized, that means the compound the reactant that started with gold is going to be my reducing agent. So I could say just Au as a solid is the reducing agent. And likewise, for my oxidizing agent, if oxygen was reduced, it's specifically the oxygen that is getting reduced, so the O2. The water is not our oxidizing agent here because oxygen's already minus 2 there. So it's this oxygen, the O2, that is our oxidizing agent. All right, so that's kind of the first thing here. Now, in terms of trying to balance this as a normal redox reaction, it almost doesn't work with the normal rules that we're accustomed to. And the main reason for why that is the fact that we have sodium and cyanide kind of here, right? And sodium and cyanide are both here, but we also have NaOH. Like, how do we break this apart into the half reactions? We can't really get away from the fact that all the cyanide and the gold and the sodium are in this one compound, which will leave only water in the other one, but there's still sodium. And so it just doesn't really work with our normal kind of way that we split things up. And a lot of that's the fact that we're making this kind of complex ion. In reality, probably what's truly going on here from a redox standpoint, like the real true half reactions for our oxidation reduction are really gold going from like gold 0 to gold plus 1, and O2 going to basically O with a -2 charge, right, for its oxidation state. Like that's really kind of the half reactions involved. The other pieces are just kind of counter ions in everything. And so we could look at this point, and really for anything that we're doing calculations on, like out of our electrochem chapter, what we'd really care about is just, what's the number of electrons being transferred, right? And so we could figure that out, like the moles of electrons being transferred, to be able to use in like the Nernst equation by just figuring out how many total electrons are being moved around. Well, if gold is going from 0 to +1, that takes 1 electron, but to go from oxygen O2 to O2 minus, and really if we're balancing that, that would be 2 oxygens that have to go to the 2 minus charge. That actually means that I need 4 electrons to do that, which means when we go to balance everything later, I'm going to have to end up having like 4 golds plus 4 is going to 4 gold plus 1, plus then 4 electrons, so that I have like 4 electrons in everything when I go to balance. Like that would be really what we have to identify out of that reaction. That's not something I'd expect you guys to be able to do for a reaction that complex for general chemistry. So I wanted to show kind of the example that was kind of given there, but I think that's kind of what I wanted to touch on. Now, in terms of is balancing redox going to be in the final exam, it's about 50-50. I've seen years where ACS has included balancing redox examples and years where it hasn't. Most of the time, it's going to ask like, it'll ask in the form like it'll give you like maybe, something. Let's say we have. It'll give us an unbalanced reaction of, let's say, MnO2 plus SO4, 2 minus, going to SO3, 2 minus, plus MnO4 minus. And it'll say, what's the coefficient in front of the MnO2? And so that's how they can make it a multiple choice question. All right, well, to show balancing redox, just to do a review, so I kind of, stay with that kind of so we can see another example. This is a more traditional one. This one is a lot easier to break apart. Right? I'll have MnO2 going to MnO4 minus, and SO4 2 minus going to SO3 2 minus. Right, now I can balance the elements that aren't oxygen or hydrogen, which is easy. Those are already done for me. Right, manganese, manganese, sulfur, and sulfur. I can balance the oxygens, so 2 waters in the top reaction on the left, 1 water in the bottom reaction on the right. Then I can add my H+, 4H+ on the right for the top reaction, 2H+ on the left on the bottom reaction. And then I can balance charge, or for the top reaction, I go from neutral to a total of +3 because I have the minus and 4 positives. So +3 electrons on the right side to balance all my charge. Bottom reaction, here I have the neutral, here I'm -2, so I'm going to need 2 electrons on the left so that I have -2 on both sides. And now to put these things together, I do need to multiply these by coefficients. Right? If I have 3 electrons and 2 electrons, I can multiply everything in that top reaction by 2. So I'm going to have 4, 2, 2, this will become 8, this will become 6. And then in the bottom, multiply everything by 6. So I'm going to get 6, 6, 3, 3, and 3. And now I just go through and add and cancel everything. Right? So cancel out the 6 electrons for each. I have 8H+ on the right, 6H+ on the left, so all the ones on the left are gone. It's going to leave me 2H+ on the right. 3 waters on the right, 4 on the left, so all the ones on the right are going to cancel. I have just a single water on the left. And now I just write what's left. Right? I'll have H2O, 2 MnO2, plus 3 SO4 2 minus, going to, this will be 3 SO3 2 minus, plus 2 MnO4 minus, plus 2H+. Right, that would be my full balanced reaction at the end of all of this. Now, this final answer would be for an acidic solution because I have this H+ over here. So this is my answer for acidic. If I wanted a basic balanced equation, now I'm going to add hydroxides to both sides to cancel out the H+ that I have. So 2OH minus to each side. Well, if I do that, that's going to leave me with 2OH minus. Well, let me not get ahead of myself. Over here, these two things will combine to make 2 waters, one of which will cancel out the water on the opposite side. So at the end of all this, I'm going to have 2OH minus plus 2 MnO2 plus 3 SO4 2 minus is going to 3 SO3 2 minus plus 2 MnO4 minus plus 1 water. That would be my balanced reaction if I was in a basic solution instead. So you get kind of like, for basic solutions, you just get this added kind of 2 steps at the end. We add OH minus to both sides, make your waters, cancel the waters out, and that'll get you your final balanced reaction. But those are your general steps. Again, I don't know if they'll actually make you go through and do all of that on the ACS exam or not. But I definitely would want to be able to recognize like what's oxidized and reduced. Well, since I've gone through and wrote out my half reactions, since I'd had electrons in the product side of this manganese part, that means the manganese must be getting oxidized, right? Because it's losing electrons. The sulfur here is what's getting reduced because I have electrons on the reactant side. I'm adding electrons to it. And so I can pick out what's oxidized or reduced that way. And that would also mean that my MnO2 is going to be my reducing agent, right? Because it got oxidized. And my SO4 is going to be my oxidizing agent because it's what got reduced, the sulfur, and it got reduced. And so I can pick out those pieces from those reactions. All right, so I think I have 2 more examples left, if I remember right. No, maybe 3. Good. 3 more examples. Take a look at kind of one each on these different topics. So here we're going to look first at colligative properties. So for colligative properties, this example is going to involve freezing point depression. We have a 7.85 gram sample of a compound with an empirical formula of C5H4 that's dissolved in benzene. We're told the freezing point of the solution is 1.05 degrees Celsius below that of normal pure benzene. And it asks what are the molar mass and the molecular formula for this compound if the Kf for benzene is 5.12 degrees Celsius per mole. All right, so freezing point depression. In general, freezing point depression is a change in freezing point that's going to be equal to negative I times Kf times little m, which is our molality. So how does this all help us? Right, we're looking for molar mass and eventually molecular formula. Molar mass is not part of this equation. But where would the molar mass fit into all of this? Well, we're given Kf, and for I, if we have an empirical formula at C5H4, this is all covalent. There's no ions there. Right? Benzene is also C6H6. It's covalent. So I in this case is going to be 1 because we have no ionic compound breaking apart into different pieces. We have the change in the freezing point, so we can solve for the molality. So we can start this problem by solving for that molality piece. Right? And so our molality is going to equal the change in the freezing point over negative I times Kf. The change in the freezing point they said was 1.05 below, so it's negative 1.05 divided by, this will be negative 1 times our Kf that they gave us, which I think was 5.12. Yep, 5.12. And so I can find our molality. And it's about 0.205 molal. But what does that really mean? That little m for molal really means moles of our solute divided by 1 kilogram of solvent. Right? That's the ratio that I should have. But what else do I know? I know that in this particular case, in 301 grams of benzene, I actually have 7.85 grams of this compound. So what I can do is I can actually use this 301 grams of benzene, which is my solvent, and I can actually make a ratio to figure out how many moles of my solute are in 301 grams. Right? So effectively what I can do is I can take 301 grams of benzene and say that put it into kilograms, which will be 0.301 kilograms of benzene, times the fact that I have 0.205 moles of my solute for every 1 kilogram of benzene. Right, why did I do this? This gets me my moles of my solute that should be in this exact solution. So 0.301 times 0.205, I get about 6.17 to the minus 2. That's how many moles of my solute I have. All right, and so now if I want to find the molar mass, what are the units normally for molar mass? They're typically grams per mole, right? Well, in the problem, they told us we have 7.85 grams of our compound. And from our molality that we found and the amount of benzene that we used, we know there must be 6.17 times 10 to the minus 2 moles of our compound. And so if I take the grams divided by my moles, that should give me a molar mass. and I get about 127. And now, how do I convert this into a molecular formula, right? So there's my molar mass, right? So to get my molecular formula, I have an empirical formula, which is the lowest ratio of things. So let's find the mass of the empirical formula first. So C5H4. So that'll be 5 times 12 plus 4 times 1, roughly. Right, it's about 64. Right, if I take the molar mass, which is 127, divided by the empirical formula mass, it's almost exactly 2. It's just a tiny bit smaller than 2. So what does that mean? That means in order to get the molecular formula, I'm going to take that ratio of 2, and I'm going to multiply my subscripts in the empirical formula by that ratio of 2 to get the molecular formula. So my molecular formula, oops, can't spell, molecular formula should be C10H8. And those are my two then answers on how I can go through that. Okay, a couple more examples. There's a few more examples here as we're getting to the end. A couple more things. Solids and band theories. This is kind of a review of just really kind of how we view like conductors versus semiconductors versus insulators, kind of from a visual sense. So in this one, I was asking about the diagrams. Like the diagrams for these typically always just show everything as bands, right? And so you have like one that's typically filled in, one that's empty. And the way this works, the top band is what we refer to as the conduction band. The bottom band is what we call the valence band. Usually the conduction band is empty, and the valence band is full of electrons, normally. And what we look for as far as like is something a conductor, an insulator, or a semiconductor, it's all about, sorry, I'm over here writing this band and have it like half hidden. So if we're talking about this kind of setup, for our conduction band, we want electrons to be able to move from the valence band to the conduction band in order to have conductivity in our large-scale solid material. That only happens if this gap is reasonably small. If this gap is really big, it's hard for electrons to make that gap, and so or jump that gap with just normal thermal energy from whatever the temperature is. And so we, as a result, we get insulators if this gap is very big. If the gap is tiny or almost non-existent, which is what happens for a lot of metals, then we have something that's a really good conductor. And so in terms of kind of visually, the way these diagrams often get represented, you'll often see things shown where you have basically no band gap. This would be a conductor, which typically is going to happen for metals, where there is no band gap. We have semiconductors, where we have a small gap, and these are typically going to be made by like our metalloids or semimetals on the periodic table. And then we have kind of our last possibility, which is if that gap is really big. Let's say we have a big gap, and we refer to this as a band gap specifically. So if we have a big gap here between what's full and what's empty, now we have what's called insulators, and these are typically made by our nonmetals. And realistically, if you understand just that much about band theory, that's probably going to cover the majority of things that would pop up with it on an ACS exam. Occasionally, you might see something about doping. And the whole purpose of doping is we have two types. Just to review those real quick, we can have p-type or n-type doping for semiconductors. For p-type, we basically just add some element that has less electrons. For n-type, we add something that has more electrons. So for instance, if silicon is our semiconductor, then that means I could add phosphorus. Right? Phosphorus is one spot to the right of silicon in the periodic table. This would get n-type doped semiconductor. Or I could add aluminum, which is the other side of it, has fewer electrons, and get p-type for the semiconductor that I would create. And the purpose of this doping, and like the different types, like n-type, p-type, is just it makes conductivity better. And the way it does that is it basically just kind of alters this gap. If you make something that has p-type, it's got fewer electrons, your gap isn't this whole jump here. This thing's not all the way full at the bottom if I'm missing electrons from some of my atoms. And so it becomes a very small energy gap to navigate. And so it becomes a better conductor because of that. N-type works in a similar fashion. It has extra electrons, so some of this top part's already full. So the energy gap between what's full and what's empty is smaller, and it's, again, a better conductor. So that's kind of probably the quick nutshell review of all of the things we really need in terms of to understand really about band theory and kind of about semiconductors and things of that sort. And so like here I give, like, I think this was the exam question, I give one pure element that could make this type of bulk solid for a semiconductor, right? And then also give an element you would add to make it a p-type semiconductor. So for the semiconductor part, silicon's probably a really common one. If I want p-type, I want something with fewer electrons, I could add aluminum. If I chose, like, something like germanium here would be another possibility. Germanium, again, kind of same thing. I want to stay in the same row, go fewer electrons. I could go one to the left, and that's going to be gallium. So I could add gallium to germanium and also get a p-type semiconductor that way. So hopefully that's a kind of quick review of some band theory stuff from the start of the semester. Now, one last example to kind of wrap up with, and this is actually more recent. Right? This is Nernst's equation. So here we're told that a standard EMF for a cell is 1.10 volts. Find the EMF of the cell at 25 degrees Celsius when the concentration of copper 2 plus is 5 molar, and the zinc concentration is 0.05 molar. So a couple things here. First off, we're going to need what reaction is happening. So the fact that it's not given with this problem makes this problem a little bit harder, probably a good review. Right? So if I have copper 2 plus, we're told its concentration is 5.00 molar, which is a pretty high concentration. We have zinc 2 plus, which has a concentration of 0.050 molar, a little bit lower. And this standard cell potential, we're given that, but also we could find that once we figure out what our reaction is. Right? So if I have copper 2 plus and zinc 2 plus, if you're not given the actual reaction, you want to look in probably your chart of standard reduction potentials and just find where these two ions show up, because there's only one reaction for each of these ions will be in. And those reactions are going to be Cu2 plus 2 electrons going to Cu solid. This thing has a standard reduction potential of 0.34 volts. And then there's going to be one that's a zinc 2 plus 2 electrons going to zinc as a solid. Its standard reduction potential is negative 0.76 volts. And so based on these voltages for the standard reduction potentials, copper has the higher reduction potential. This is the reduction reaction that'll happen. The reverse for the zinc is going to happen, or it's going to get oxidized instead. So our actual reaction is going to be copper 2 plus 2, I don't even need the 2 electrons. Right, copper 2 plus zinc as a solid, going to copper as a solid plus zinc 2 plus. Right, that's our balanced reaction. Now, why is that important? Because if I'm going to solve something about what my actual cell potential is from a standard cell potential, I have to use the equation of E cell is equal to E naught cell, right? Oops. Minus, since I'm at 25 degrees, I can go ahead and use this version, 0.0592 volts over N times the log of Q. And that's the important part, right? In order to find Q, I have to know the balanced reaction. Well, zinc and copper are solids, so my Q in this case is going to be my concentration of zinc 2 plus over the concentration of copper 2 plus. And at that point, now I have all of the pieces really that I need. Right? I have the standard cell potential they gave me. I'm at 25 degrees, so that's why I was able to use this version of the equation. So I do need to know N, but if I'm looking again at my reaction I just wrote, another part why the reaction matters, it's 2 electrons that are being transferred. Copper's gaining 2, the zinc is losing 2, so the N is going to be 2, and I have what I need here to find Q. Right? I have those concentrations, 5 molar for the copper, 0.05 for the zinc, so it'll be 0.050 over 5.0. So my Q in this case, what is that, 0.01? Oops, don't need a unit. So there's my Q. So if I want to find my cell potential out of all of this, it's going to be equal to my standard cell potential, 1.10 volts that they gave, minus 0.0592 over 2, times the log of 0.01, which the log of 0.01 is just going to be, I believe, -2. Nope. So at the end of all this, I get a cell potential that looks like it should be about 1.16. Right? And because this log of 0.01 is negative, I'm going to get basically out of all of this as I'm putting things together, like it's minus this chunk, but since this is -2 times all of this, well, that's then effectively become a plus because I have the two negative signs. So that's my final cell potential. So this is using our Nernst equation, but we want to recognize these other pieces, right? We want to recognize what our reaction is based on the ions that were there, and kind of using our standard reduction potential table to help us find. And that's where the 1.10 volts even comes from, right? I have 0.34 volts for the copper, -0.76. So the bigger reduction potential minus the smaller one is kind of the way you're always doing it. So 0.34 minus a -0.76 is the 1.10. And then I can write my reaction, which is important to get the states so that I get the right equation for Q. To kind of go through everything. But that kind of gets us to the end, I think, of all the different example problems people gave for the review. I don't know yet my times. I'll probably make a post sometime this evening about what my office hours will look like tomorrow, because they're probably not going to be the standard hours that I normally have. I'll probably have longer available office hours. I just don't know what they're going to be yet. I'm unfortunately going to have to be traveling a little bit during the day tomorrow, so I don't know when exactly they're going to be. They're probably going to be later afternoon and evening. But I should be available for some windows here, hopefully, to help answer questions for people. Feel free, if I'm not available at a time that you're available, send me emails. You can email me either specific questions or general questions. I'll be happy to help respond. But I am going to have a post probably up on D2L here shortly as well. That'll be a last little thing that's a printout basically for the ACS exam that you can have, so that you have kind of like an equation sheet and a periodic table and things like that as well. And I'll make sure that's in the kind of next update post that I send out for everyone. But that's all I have for this time. Hopefully these videos of kind of walking through these review problems that people have asked about have been useful. If you want to see more examples of them, or if you still have questions, like I said, please email me. You can stop in the office hours I set up for Monday, so we can hopefully kind of get some last questions answered here before we get to our final exam that's somehow snuck up on us already. But I hope everyone's had a good weekend, and I will kind of talk to everyone here as we finish up.